Hello, this is Professor Kuehn. Welcome back to my lectures on electricity, magnetism, and light, where we are looking at the Lectures on Light by John Tyndall. We have made our way up to chapter 23 in A Student's Guide to the Great Physics Text, volume 3. This chapter is on crystal symmetry and light rotation. We'll be specifically looking at how light propagates through birefringent crystals, such as Iceland spar or calcite. So let's just remind ourselves where we've been, and then we'll make our way into this chapter. So one of the first things that we were concerned about when studying Tyndall was the notion of light as a transverse wave. So let me just remind you the idea here is that when light comes from a source such as the sun, the light is said to be unpolarized. What does that mean? Well, if I were to draw a coordinate system like this, and the light was traveling in this direction, let's suppose it's traveling along the z-axis, and we'll call this the x and the y-axis. Well, the light that is coming from the sun is generated by vibrating atoms that comprise the sun, and as these vibrate, they're all vibrating in kind of random directions. This is the kinetic theory of heat. The sun is hot, all these atoms are vibrating in different directions, and as a result, they're producing light that has all different polarizations. So we might imagine there is light that's vibrating kind of up and down like this. There's also light vibrating back and forth like this. But there's also light vibrating in all different orientations, kind of randomly vibrating in all different ways, so that if you were to look straight at this sunbeam coming at you, which of course you probably shouldn't do, but if I look from down the z-axis, so if you were to look from over here down the z-axis so that you're looking at my diagram I've just drawn in the upper right corner here, well, the vibrations of the transverse waves would be back and forth like this. They would be up and down like this, but they would also be in every different orientation. There would be this random kind of distribution of vibrations of light in all different directions. Here's the important thing, though, is that the ones that are vibrating back and forth along the x-axis, we can call those linearly polarized along this direction. The ones that are vibrating perfectly along the y-axis can be considered to be linearly polarized along this direction. So that is x polarized and y polarized, or if you like, horizontally and vertically polarized. I prefer to use x and y polarized. But also the diagonal ones, although they're diagonally polarized, those can be kind of decomposed into components that are along the x-axis and components along the y-axis. It's almost like if you're considering any kind of quantity, like if someone is walking in the northeast direction like that, you can consider that, you can decompose that into a component that is in the east direction and a component that is in the north direction by kind of projecting this orientation onto these two axes. So knowing how much is in the east and how much is in the north direction, you can amply describe this diagonal direction. It's very similar for light. If we consider diagonally polarized light, you can break that down into a horizontally and a vertically polarized component. So that's why it's usually convenient to talk strictly about the X polarization and the Y polarization. Okay, that's just by way of some background, and those are going to be some important concepts that we're going to need to draw upon in this chapter. Now, remember, let's recall here. So recall that initially unpolarized light, like coming from the sun, initially unpolarized light can be polarized, and there are a few ways that we talked about. The first way that we talked about is by passing the unpolarized light through a sheet of tourmaline crystal. And what that does, the tourmaline acts as a filter that only allows one direction of polarization through. So if I wanted to, I could take this unpolarized light, I could put a sheet of tourmaline right here, and if the tourmaline is oriented in a certain direction like this, only the vertically polarized or the Y-polarized component of that light would make it through. So that's one way that in chapter 22 we talked about of polarizing light. Another way is by reflecting the unpolarized light off of a mirror or glass at a particular angle, that is at Brewster's angle. And this gives rise to completely polarized light as well. So those are the two ways that he talked about of achieving polarized light. Now, at the beginning of chapter 23, Tyndall is going to talk about another ingenious method of polarizing light, and this was developed by a man named Nicol, and he developed something called a Nicol prism, or a Nicol crystal. This is described in the second full paragraph on page 270. He mentions that an able optician named Nicol cut a crystal of Iceland spar in two halves in a certain direction. He polished the severed surfaces and reunited them by Canada balsam, the surface of union being so inclined to the beam traversing the spar that the ordinary ray, which is the most highly refracted, was totally reflected by the balsam, while the extraordinary ray was permitted to pass on. That is depicted in this picture, figure 23.1. So let's spend a few minutes trying to understand what he's talking about. So I'm just going to write down here the third method using what's called a Nicol crystal. What is this Nicol crystal? Well, it is able to achieve, by the way, he says, achieve a very purely polarized light. So this is one of the most purely polarized, or you're able to achieve the most purely polarized light using this technique. Even better than using tourmaline. So let's remind ourselves of how Iceland spar works. So it's going to take a couple of drawings here. So let's suppose we had a crystal of Iceland spar. I know it's a rhombus, but I'm just going to draw it as a square because it's a little bit easier to draw. And if we have a ray of light coming in, that ray of light is broken up into two beams. And let's call this one the ordinary beam, and the other one is the extraordinary beam. I'm only going to draw the refraction at the first surface. My point here is merely to say that it breaks into an ordinary and an extraordinary beam. And remember the difference between these. The ordinary beam is highly refracted. It's bent a lot. It obeys the ordinary law of refraction, or highly refracted, I would say. It behaves as if the crystal had a refractive index. The refractive index for the ordinary beam was 1.654. And by the way, the ordinary beam is comprised of polarized light. It's polarized in a particular orientation. So I'll say polarized in one way with respect to the crystal axes. This is something we explored a bit in lab. And then there's the extraordinary beam. And this is less refracted, it's less bent. And at best, you can have a refractive index, well, at lowest, you might say, of the extraordinary beam of 1.483. So you can have a very low refractive index. And by the way, the extraordinary beam is polarized in the other way with respect to the crystal axes. So in other words, this initial light was initially unpolarized light. So I'm going to kind of draw a little X here, meaning it's unpolarized. It has both polarizations. And the ordinary beam is comprised of light polarized in one orientation, and the extraordinary beam is comprised of light polarized in the other orientation. And you can see this by holding a polarizing filter and seeing these two different polarizations. Okay, so that's one piece of knowledge that we need to have in order to understand how the Nicol prism works. The other piece of information, the other ingredient we need to understand, is total internal reflection. So recall total internal reflection. When does total internal reflection occurs? It occurs when a high refractive index medium is surrounded or bounded by a low refractive index medium. So let's suppose that we have a boundary between two media, okay? And let's suppose that this one is Iceland spar or calcite, okay? And remember that if we have, I'm going to draw a couple of beams here. If we have the light coming, and by the way, let's call this air out here, or let's call this balsam fir sap, or balsam sap, the material that he used. And the balsam sap has a refractive index of, let's say, about 1.5. I don't know exactly what it is, but the point is going to be that it has a lower refractive index than the Iceland spar, at least for the ordinary beam, 1.654. That's for the ordinary beam. Okay, so let's suppose we have an ordinary beam and it's coming in at an angle so that as it bends away from the normal, it bends away from the normal so much that it doesn't make it out of this Iceland spar into the balsam sap, and as a result it bounces back into the Iceland spar. That is a phenomenon of total internal reflection, right? So there's going to be some angle of incidence that it makes so that it is unable to make it out into the balsam sap. Okay, so this is the, I guess we'd say this is the behavior of the ordinary beam. And it only works like this because the balsam sap has a lower refractive index than the ordinary beam. It has a lower refractive index than the Iceland spar for the ordinary beam. Now, what about if instead of using this ordinary beam on the surface, okay, so here's the ordinary beam in orange, let's suppose that we had both beams, the ordinary and the extraordinary beam. So I'm going to draw the extraordinary beam in yellow, like this. Now keep in mind that the refractive index of the Iceland spar for the extraordinary beam is 1.483. That is, the refractive index is less than the refractive index of balsam sap. And as a result, when it impacts the surface, it bends in the other direction and it makes it into the balsam sap. So this would be the extraordinary beam. So if you have both of these beams, the ordinary and the extraordinary, incident on an interface between Iceland spar and balsam sap at just the right angle, you can separate them into a part that's reflected back into the Iceland spar, that is totally internally reflected, and that would be the ordinary beam, and a part that is transmitted into the balsam sap, that is the extraordinary beam. This provides a very nice and clever way to greatly separate the two polarizations of light that are coming through the Iceland spar. The polarization that's associated with the ordinary beam and the polarization that is associated with the extraordinary beam. That is exactly the point of the Nicol prism. So what Nicol did, as mentioned by Tyndall here, is he took a piece of Iceland spar and he cut it in just the right way. And I'm exaggerating the separation here a bit. And then he smeared some of this balsam sap in between the two parts, like this. So here he had this balsam sap, a sap of a balsam tree. And these parts here on the edges were the calcite or Iceland spar. And now you might imagine if we have these beams coming through like this, and are incident upon this interface. So this is both beams, the ordinary and the extraordinary, let's say, are going through the balsam, through the calcite. You can have a situation where the ordinary beam bounces off like this, and the extraordinary beam makes it through into the balsam sap like this. Okay, so you can separate out these two beams very efficiently. That is the point of the Nicol prism, and that is what he's depicting in figure 23.1. Okay, so I'm going to stop there. Next time what I'm going to do is I'm going to spend some time talking about the colors of films of selenite in polarized light. This is a little bit of a challenging thing to understand, but it's directly responsible for the kinds of things that you saw in lab this past week when you held two crossed polarized filters and held a piece of mica, a thin sheet of mica between them, or when you held some cellophane tape, and it was perhaps most obvious in this case, when you put cellophane tape on a sheet of acetate between these two crossed polarized filters, you saw these beautiful colors appear. And so the question is, how can we understand that? That's exactly what Tyndall is going to be talking about on pages 271 and the following pages.